This is section 9.2. We're going to compare more than two proportions, and we're going to use a chi-square test to do it. So to start with, we're going to do a simulation first, okay? And I want you to remember in chapter 6 how we would compare proportions for two groups. But what if our explanatory variable has 3 or maybe even more groups? So for example, we have this organ donation study where our first step is the research question. So someone wanted to know, they said, organ donations save lives. And surveys show that many Americans approve of organ donation, but the problem is we have a hard time recruiting them. Sometimes people don't actually want to have to make that decision. Okay? So we're wondering, could wording the question differently change people's willingness to become a donor? So can you word the question differently to change whether or not they'll sign up to be a donor? So step 2 is design a study and collect data. So they have the study where they ask people to imagine that they're moving to a new state and they're applying for a driver's license. Okay, they recruited participants through various interest boards on the internet. Okay, so this part tells you that it's not a random study or not a random sample. And they offered an incentive $4 to get people to actually do it. Okay, so the fact that it's not a random sample and they were paying people to do it tells you that it's not going to be representative of all people. Now, as part of this application, they were told to decide whether to become an organ donor. Some people were randomly assigned. So they're randomly assigned to be told one of 3 options. So they could opt in. So they were told that the default was to not be a donor and they had to opt in if they wanted to be a donor. They could opt out, where they were told the default is that you had to be a donor and then they had to opt out if they didn't want to do it. And then there was neutral. There was no prior option. They were just asked if they wanted to donate, be an organ donor. So that was randomly assigned. Okay. And that's important. That tells us that it's going to be an experiment because we chose which group the people are in. Okay, and we randomly did it. Then researchers counted the number of individuals in each group that said they would be organ donors, excluding careless responses. That means if they took less than 5 seconds, and multiple responses from the same IP address, so if someone just took it over and over to get $4 each time. We want to know if there's an association between type of question and whether someone signs up to be an organ donor. Now, let's remember from chapter 6, association does not mean cause and effect. Association just means that the two variables are somehow related, that knowing information about one can give us information about the other. So first of all, is it's an observational study, a randomized experiment? Well, we already figured out it's an experiment, and it was not a random sample. Okay, let's see, what are our experimental units? What are we collecting data on? We're collecting data on each individual in the sample. And what is the sample size? Did they tell me the sample size yet? I don't actually think they told me the sample size. Sometimes you have to scroll up. So maybe let's scroll down, okay, just a little bit. Into this table, you can see that we had the opt-in, opt-out, and neutral groups, and then if they were donor or not. And this total right here is how many people you had in the whole study. So that was 161. Now for our explanatory variable, what are we trying to use to explain something? Or what groups did we put people in? We put them into the type of question group. That's what we're trying to use to explain it. And what are we trying to predict or explain? It's whether or not they will be a donor. Now, once we have each variable, let's classify it. So explanatory variable, the type of question, there were 3 options: opt-in, opt-out, and neutral. So it is categorical with 3 categories or 3 groups. Okay. Whether or not they will be a donor, well, that's also categorical. And it's what we can call binary because there's only 2 categories. And to explore the data for step 3, we use two-way tables. Remember, our size is number of rows by number of columns. We say this, use the word by when we say it out loud. And we don't count the totals. So our actual data is just this part right here, or specifically 3 rows, 2 columns. That's our actual data. We don't count the totals. We don't count the headings. 3 rows. Sorry, I said that wrong. There are 2 rows by 3 columns. So it's a 2 by 3. Now we need to go to our ISI applets. We're going to go to categorical and multiple proportions this time. And for this one, the donor data is actually the default data right here. We can just do organ donors and we can click use data. So when it gives us my raw data, I click use data. Later we're going to show you what to do if we give it to you in a table. I could have also clicked this enter table and I could choose that I want a 2x3 table and I can type everything in by hand. Okay. But since it's already in there, let's just do that. So organ donors, let's use the data. Okay, so here's my data here. You'll notice when I did it like this, it said my success is not a donor. We probably want to switch that to say our success is a donor, and I'll just put donor first. It just looks a little bit better to us. We'll click show table, and this is now our observed table. It looks very similar to what we did back in chapter 2. This whole applet, or chapter 6 with 2 proportions. This whole applet should look fairly familiar. Okay, so we can get bar graphs and segmented bar graphs and mosaic plots. Okay. Looking at this bar graph, I can see that the opt-out and neutral groups, these are fairly similar, okay? But the opt-in group, notice how much lower it is than the other groups. Okay, you see the same thing in mosaic plots. Remember, mosaic plots just adjust the width based on the sample sizes, but our sample sizes of 55, 50, and 56 were all pretty similar, so you don't really see a big difference there. And in this show table, this observed table, it will give you all the data, okay, and then it will give you the conditional proportions. So like what proportion of the opt-in group chose to be a donor? Well, that would be p hat, and I'll write in for the opt-in group is 0.418. And what proportion of the opt-out group chose to be a donor? Well, that would be the sample proportion. I'll write out here. And if I wanted to calculate it by hand, I could do it as 41 out of 50. So 41 out of 50, or 0.82. Okay, and what proportion of the neutral group? Well, now I want the neutral group. So the sample proportion for the neutral equals 0.786. Now, what should the segmented bar graph have looked like if there was no association between the type of question and whether or not there was a donor? Well, if you think about it, if there was no association, okay, then we should have had something where the bars were all equal. Okay, so sorry, it's a segmented bar graph, so it should have looked like this. So all the bars were the same height. That's what you'd expect if there was no association. You'd expect each group to have the same proportion. So we'd expect each group to have the same proportion of donors if there is no association. So now looking at our conditional proportions and our bar graphs up here, what do you think? Do you think these bars are all the same height? I would say looking at them that these two are again pretty similar for out and neutral, but for the opt-in group, it is much lower. So I could say something like the opt-in is much lower, so I think there is an association. So now let's make inferences beyond the data. Okay, so we said that there's a difference. We said that the opt-in group is a bit lower, but is that going to be a significant difference? Okay, so we know there's a difference in the conditional proportions in our sample, but would there be a difference in the conditional proportions for the entire population? So for the population, we could use these symbols. We could say that pi, remember this is pi for our population proportion. So we can say the population proportion of people in the opt-in group is this pi in. And we can do pi out for the population proportion of people in the opt-out group that choose to be a donor, and pi neutral. So the null hypothesis, we can say it in words or we can say it in symbols. So if we want to do it in words, we say the null hypothesis is that there is not an association between the type of question and whether or not they want to be a donor. Okay. If I want to say it in symbols, I'd say pi in equals pi out equals pi neutral. So we're just saying that the population proportions or the conditional proportions are the same for each group. The alternative hypothesis is that there is an association between the type of question and whether or not to be a donor. Now the problem is, how would we write this alternative in symbols? Okay, so maybe it's that the proportion for in is different than the proportion for out. Or maybe it's the proportion for in is different than the proportion for neutral. Or maybe it's that they are all different. That's something that's really hard to write out in words. It takes a lot longer than we ever want to do. So we'd probably say something like at least one of the, and then I just switch back to writing symbols, pi i's. So just one of the population proportions. So at least one of the population proportions is different from. So we're not trying to say which one is different. We're not trying to say whether one is different or they're all different. We're just saying at least one of those conditional population proportions is different from the others. Okay. Now, same thing we've been doing the entire semester. The first step of the 3S strategy is to specify a statistic. So to compare two proportions, we found the difference in sample proportions. But now we have three proportions. So we could compare all of the possible pairs of conditional proportions. So like if I want to do opt-in versus opt-out, okay, I'd say, okay, well, what was the sample proportion for in? And then I'll minus the sample proportion for out. Okay. And I have to scroll back up to see what those are. So it looks like it would be 0.418 and 0.820. So 0.418 minus 0.82. That gives me negative 0.402. And I could do that for each of the other pairs. So I could still find the difference between opt-in and neutral, so negative 0.368, and the sample proportions between out and neutral, so 0.034. Okay. But that's three differences. So how can we choose just a single statistic for just one number that we can measure the strength of evidence against the null hypothesis? Okay. And so there's quite a few different options we could use. One that the book talks about in section 9.1 is called the mean group difference. So they want to add up each of these differences. Okay, so we want to add up each of the differences. Okay. The problem though is some of them are positive and some of them are negative, and those positive and negatives can cancel each other out, and we don't want that. Okay, so we're going to take the absolute value. So we take the absolute value of each of the differences, and then we just divide by 3 because there were 3 pairs. So that is one thing that we could do to try and get one number. Okay. The problem is that doesn't have a theory-based approach, so it is not used widely. Okay, so we're going to use what's called a chi-square statistic instead. It's very famous and actually has more than just one application. Like there's another application in section 9.3. Okay, again, very famous. You'll definitely see this in science classes if you ever take science classes or other classes that do any kind of research. Okay. So how do we find the chi-squared statistic? The null hypothesis is that there's no association between the variables. The alternative is that there is an association. Okay, so if there were no association, and the 108 people that would have been donors were just randomly put into the 3 groups, then we'd have an overall proportion of donors. We can just say p hat. So if you look back up our table, there were 108 total. Let's go up. There were 108 total donors out of 161 total people. Okay. So this is the overall proportion of donors, is this 108 out of 100. And so we get 0.67 overall that are donors. Okay. And so if overall 67% of people were going to be donors, and there were 55 people in the opt-in group, then we would have expected about 0.67 times 55, or 36.89 people to be donors in the opt-in. Again, assuming that there's no association. Okay, that's how many we would have expected if people just randomly put into each group. And we can use this logic, and that gives us this formula of the expected count, how many we expect it to be in that cell, is going to be our row total times our column total over our grand total. I am not going to make you do this by hand, ever. I just want you to understand where it's coming from, but you don't have to actually really understand any of this math because the applet's going to do it all for us. Okay. That will let us find the expected counts, again, if there's no association for each cell in the table. So if there was no association and we'd really just randomly had 108 donors and 53 not donors, and we randomly distributed them into 3 groups, we would have expected these following counts. Okay, so here's our observed counts. That's our actual data. And then in this other table, we have our expected counts. Okay, so we got 23 donors in the opt-in group, but if they were all just randomly distributed, we would have expected 36 or 37 people being in the opt-out group that were donors. If, again, there was no association, it was like we just randomly put them all into groups. So now we need a way to compare the counts we got and the expected counts, and we want to account for sample size. So what we do is they came up with this chi-squared statistic. This is the Greek letter chi. And we always say chi-squared. Okay. So chi-squared is going to be the sum of, we're going to take each observed value minus expected value, square it, and then divide by the expected. Okay, so for our data, what we do is we'd come up here and we pick the cell, which had 23 people. Okay, and then we minus the expected count of 36.89. We square it, and then we divide by 36.89. Then we go to our next cell. We do 41, so that's our observed. Okay, and then our expected was 33, so we minus the 33, and then square it, and divide by the 33.54. So we have to do that for every cell. You can tell this would take a long time to do by hand. So I'm not going to make you do it by hand at all. You don't have to understand this. What you truly have to understand is this concept of when we were comparing, we squared everything. Okay. That's important because if we square everything, can the chi-square statistic ever be negative? No, because we squared each piece. And so the fact that it can't be negative is going to be important later on. Okay, and it can't be negative because we squared each difference up here. Now, if our population proportions were the same for each group, we would expect a chi-square statistic close to what? Okay, so let's think about it. If these were our expected counts of if the population proportions are the same, okay, and so if our actual data had come from a place where the population proportions are the same, we'd expect the actual data to be close to the expected counts. And so these differences would be really close to 0. So each of the differences would be close to 0. When we add them all up, we should still get something close to 0. But if our population proportions are different from each group, then we're going to expect our observed counts to be far away from our expected counts. Let's make a note of that here. So the observed counts would be far away from the expected counts if the population proportions are really different. Okay, and so if the observed is far away from the expected, if these observed are far away from the expected, then this number is going to get pretty big, and when we square it, it's going to get really big. Okay, and so if our population proportions are different from each other, we're going to expect a big chi-square statistic. So what types of values, like large, small, positive, negative, for this chi-square statistic will provide evidence against the null hypothesis that the population proportions are all the same, and in favor for the alternative hypothesis, which is at least one of these proportions is different. So it's going to be large, positive values. Positive, because it always has to be positive, and large, the larger they are, the farther our observed ones were from what we expected. So we're going to go to our applet. And the problem with this applet is there's a lot of different options you can use for your statistic. So you have to remember to change it every time. So you're going to go to this mean group diff and change to chi-squared. Okay. And now it will tell you this is your observed chi-squared. You can also click this show chi-squared output. Okay. And then this will come up. So let's come back and talk about what that gives you. Okay. So this is my observed table. It will tell you your observed chi-squared. That is our chi-squared statistic. Okay. And now these contributions are each part of the formula. So this 5.23 is the piece of the formula up here. This piece right here equals 5.23. Okay. So basically it's telling you each piece of the chi-squared formula. So this is what we got in one cell, this is what we got in one cell. You don't need to know that, okay? Because all you have to do is know the sum at the very end is your chi-squared equals 24.284. But it tells you that here. But that's what it is when it talks about the contributions. It's just saying this was this piece of the formula for that one cell. Okay, so now that we have our statistic, we have to actually simulate. So we got an observed chi-square statistic of 28.284 in our sample. So is this evidence that there's an association between the variables? Or could it just be the random chance based on who was in my sample and who I put in each group? So let's assume for a moment that the type of question has absolutely no effect on the response. Okay, so we're assuming that out of the 161 people, 108 were going to be donors regardless of the type of question, and 53 were not going to be donors. So we can have the applet randomly assign those 108 donors to the 3 groups and the 53 not donors to the 3 groups. Then we calculate the chi-square statistic for the shuffled data. So we're going to go back to our applet. We come over here Okay, we click Show Shuffle Options. I want to click Plot because I like the plot better than the data, and I shuffle once. Okay, so notice now it shuffled my data. You can see the bar graph looks different than it did before. Okay, I have different counts in my data because we shuffled everything up, and you can get a shuffled chi-square value of 2.44. Okay, and again, this is the contributions for each cell for the formula, and it will put my one shuffled chi-square statistic over here. Okay, if I did it again, this time I got a shuffled chi-square of 3.85. Okay, again, my bar graph, they look pretty similar as far as height. They're not exactly the same, but they are much closer. Okay, if I shuffle again, this time they're really close, and my chi-squared is really small. Okay, and I can just keep shuffling, and every time I shuffle, I get a different bar graph because I'm just distributing those groups differently, the donors and non-donors, into my groups in a different way. I get a new shuffled statistic, and I put it over here on my graph. Okay, so let's look at this output just to make a few notes. Make sure your statistic says chi-squared. If you select over to the left, it should change here too, but make sure you're looking at chi-squared and not another statistic. Okay, so this is my most recent shuffle. This is my shuffled chi-squared, and it shows up here on my plot. Okay. So as we shuffled a few more times, what did you notice about the shuffled segmented bar graphs? Remember, all of these shuffled segmented bar graphs, if I keep shuffling, the bars are usually pretty close to the same height. Okay. What about the shuffled chi-square statistics? Are they usually being larger or smaller than the one we got for actual research study, which was 28.24? So I've done it a few times. Most of them have been from about 0 to about 4.1. That's a lot smaller than the one we got in our actual data. So we could say they are smaller. Okay, and as always, we should do this at least 1,000 times. The textbook always says 1,000 times. I like to do 10,000 times so that you and I get pretty close to the same answer. Okay, but some big data sets you won't want to do it that many times. But the chi-squared one seems to go pretty fast. Okay, so now this is my new null distribution. Okay, you can see these are all of my various shuffled chi-square statistics. So it's the simulated shuffled values we got for the chi-square statistic when there's no association. You can see the mean and SD, those are the mean and SD of our shuffled chi-square statistics. Now the interesting thing here is look at this shape. What do you notice in this shape? Okay. It is skewed to the right. Okay. This is not a coincidence. This is because our statistic can never be negative. Remember how we squared things? Okay, we squared each piece, so our statistic can never be negative. That's why it looks like this. It's not symmetric because we can't have those negative values. Okay, so again, it is that shape, skewed right, because the statistic can never be negative because we squared the pieces in the formula. Now, let's assess our strength of evidence. So let's shade up here on this null distribution what we need to count to find the p-value. Okay. So just like we've done every time we find our statistic on here, which in this case, our statistic is like way over here. So chi-squared equals the 24.284. Okay, so that's where our statistic is. And then we need to figure out which way should we shade. Well, which way convinces us more that we have more evidence against the null hypothesis. So we're going to have more evidence the bigger our statistic is. That means we had bigger differences between what we observed and what we expected. So I want to shade going to the right. I want to shade out here on this right tail. So I'm going to count greater than my statistic of 24.284. So we come back to our applet. And I want to count my samples greater than 24.284. And it looks like we're about 0, which makes sense based on the picture. So it's about 0. So let's interpret that p-value. Okay. And I guess I said about 0, but it's just 0 because we're doing a simulation. Okay. To interpret the p-value, I'd say something like there is a 0% chance of getting our statistic of 24.284 or bigger if the null is true. So it's the same interpretation we've been using the entire semester. We always assume our null is true to do all of those calculations, and then the p-value is a chance of getting our statistic or something more extreme. And in our case, it would just be the 24.2 or bigger because we only cared about things to the right. Okay. So is the null hypothesis plausible? I would say definitely not. There was a 0% chance of that happening, of us getting our statistic if the null was true. Okay, so do we have evidence for the alternative hypothesis? I would say yes. Very strong evidence because it's less than 0.01. So that was all step 4. We found a statistic, we simulated, we found our strength of evidence. Now in step 5, we can write our conclusion. So our conclusion is we would probably want to say something like, we have very strong evidence that what? Okay, so now just repeat your alternative hypothesis, which in this case was that there was an association. So very strong evidence that the type of question is associated with whether or not they want to be a donor, or they signed up to be a donor. I can write it like that. I could technically also write it like this. So I could say we have strong evidence that at least one population proportion, those PIs, differs from the rest. Okay. So remember we said if the null is true, if there's no association, then the proportion of donors in each group should be the same. Okay, so the opposite of that and the alternative is at least one of them is different. We're not saying which one, we're just saying at least one is different. Okay. Do we have cause and effect? Okay. Yes, because it was an experiment with random assignment. Okay. What about who can you generalize it to? Well, this was not a random sample. So we can only generalize to similar people as in the study. Okay. And they didn't really tell me very much about them, so I don't really know what they would be like, but I can't generalize to everyone because it wasn't a random sample. Step 6 is look back and ahead. This was not a random sample. We should try again with a random sample. Okay. Also, people were only asked to imagine that they're filling out the application. Perhaps they'd respond differently if this was a real decision. Like maybe it's really easy to say, yes, I'll be a donor if you know you don't actually have to be a donor. Or maybe the type of question affects people differently based on maybe gender or religion or age or geographical location. We can investigate those possibilities. Those will all be ideas for future research. So let's summarize our simulation here. To compare proportions from multiple groups, we can use the multiple proportions applet. Okay, we use the chi-square statistic, and the p-value is always a proportion of shuffle statistics greater than or equal to our observed statistic. The null is that there's no association between your variables. Alternative is that there is an association. Okay, and just remember, again, association does not mean cause and effect. It just means somehow they're related. There could be some kind of confounding variable or something in most of these situations. We're just saying that they're related usually. Okay. Now, in our situation, we said we could do cause and effect because it was an experiment. But most of the other studies we're going to look at, we can't say that because it wasn't an experiment. Okay. Now, confidence intervals for the differences. Okay, so we're going to continue our donors example. So now that we've determined that there is an association, or that at least one of the population proportions is different than the others, you might wonder which proportion is different. Okay. So we can have the applet give us 95% confidence intervals for the pairwise differences in proportions. Okay. So that's, if you come back to your applet over here in this bottom left corner, it's the box for 95% confidence intervals. Super easy, it just gives them to you. Okay. So these are the differences in the proportions for each pair. Okay. So when we look at it, it's saying if I subtract the proportions between opt-in and opt-out for the population proportions, we're pretty sure the population proportions, the difference between those, is between negative 0.57 and negative 0.233. For opt-in versus neutral, negative 0.536 to negative 0.199. And if we compare opt-out and neutral, we're pretty sure the difference in their population proportions is between negative 0.11 and positive 0.186. Okay. Now, pretend you're back in chapter 6 again. When we looked at two groups and we wanted to see if they were significantly different, we just said, is 0 in the interval? Okay. So in this case, we want to look for things, if we want to know if they have significant differences, we want ones that 0 is not in the interval. Okay, so looking for ones where 0 is not in the interval, that would be opt-in versus opt-out. So those are significantly different. Okay, and also opt-in versus neutral. And which pairs do not have significant differences? Well, that would be when 0 is in the interval. Okay, so we looked at the opt-out versus neutral. So first we compared all of the groups together to see if there were any differences. And once we compared all the groups, we want to look at the individual pairs to see like which one actually is different. Okay. So if 0 is not in the interval, that means they were significantly different. Okay. And so we said basically opt-in is significantly different from opt-out and is significantly different from neutral. Is that what we would have guessed from our mosaic plot and our conditional proportions? So looking at this, we said, oh yeah, this one seems different than the others. Or looking at the proportions, this one seems much lower than both of the others, but these two seem fairly similar. So that makes sense to me. Opt-in is going to be significantly different than opt-out and neutral, but opt-out and neutral are going to be pretty similar to each other, so they were not significantly different. Okay, and how could I interpret each one? We could say something, and I phrased each of these. Actually, these ones are phrased about the same. There's different ways we can phrase them, though. Okay, but basically each time it's going to be we're 95% confident, and then it's just that our population, the difference in our population proportions is in that interval. But here's some ways that we can say it. So like we're 95% confident that the opt-in group will have, oh, I have to scroll back up. So 0.57 to 0.233 less, and I'm going to say less because they're negative. Less people choose to donate compared to the opt-out group. And if I'm going to phrase it like that, maybe I want to change it to proportion, so a percent. So I could just say 57% to 23.3% less people choose to donate compared to the opt-out group. Okay, so opt-in versus opt-out was this first interval right there. Okay. Now my next one is comparing opt-in to neutral. So opt-in to neutral, that would be this confidence interval right here. Okay. Looks like they were both negative as well. So we could say we're 95% confident the opt-in group will have between 53.6% to 19.9% less people choose to donate than the neutral group. Okay. And now we want our opt-out versus neutral group. Okay. So that would be this last interval right now here. Notice that one is negative and one is positive. Okay. So we're going to have 11.7% less to 18.6% more people choose to donate compared to the neutral group. Okay, so that's why A and B, those were both significantly different because we're like, oh, we're pretty sure the opt-in group is less. But when we get to this opt-out versus neutral, we're like, well, it's either less or it's more. It's not significantly different. Okay. So now let's talk about our chi-squared theory-based approach. So if our sample size is large enough, at least 10 observations in each cell, we can use the theory-based approach. Our theory-based approach uses our same chi-square statistic. It's called the chi-square test, okay, and uses a chi-square distribution to find the p-values. Okay. So our chi-square distribution also has degrees of freedom, just like our t-distribution, and it changes shape quite a bit. They're all right-skewed, but you notice they look quite a bit different. Okay, so these are the different degrees of freedom. So 1 degree of freedom is this one right here. Okay, then 2 degrees of freedom, 3 degrees of freedom, 4 degrees of freedom, 5 degrees of freedom, 6 degrees of freedom. Okay, but they're all right skewed. They just look different based on the degrees of freedom. Okay, and we need those degrees of freedom to adjust our curve based on how many categories we have in each variable. And as always, our null hypothesis is that there's no association between the variables. The alternative hypothesis is that there is an association between variables. Okay. So let's go back to our example. We're going to use the applet again, but we can click the show chi-squared output right here. Okay. Or we can come over here by the simulation and click this overlay chi-squared distribution. Okay, so click the button there, or you can click overlay right here, and it will draw the curve over it for you. Notice how well that curve fits our simulation. Okay, so nicely. So that tells you this is your theory-based p-value, okay, and this is your theory-based p-value. So it will show it in both places. So our theory-based p-value is less than 0.001. Okay, but let's check first. Should we have used this? Are our validity conditions met? So the validity conditions is you need at least 10 in each cell. Okay, so 23 is bigger, 41 is bigger, 44 is bigger, 32 is bigger. 9 was not bigger. So 9 is too small. Okay, so no, we shouldn't use theory-based. Now, on a situation like this, 9 is so close to 10. These are kind of guidelines. Some textbooks even say 5. Could you probably get away with doing it here? Probably. You won't need to make sure you put in your research paper that, oh, one group had a count of 9, but I think it's so close. Although my numbers are big, 9's really close to 10. I could probably still use the theory-based approach. Okay. But in our class, we'll just say, nope, 9's too small, so we shouldn't use the theory-based approach. But just for practice, let's go ahead and do it. So what was our statistic? Our statistic is still this chi-squared, or it will also say it here on the sum. So it's still chi-squared equals 24.284. And my p-value is less than 0.0001, which matches up what I got on my simulation. Okay. This applet will just always cut it off at less than 0.001, no matter what it is if it's smaller than that. So let's do one more example, and then we'll have another video later that has 2 more examples that you'll do tomorrow. Okay. So we have nearsightedness and lights. So a study investigated whether there is a relationship between the use of night lights in a child's room before age 2 and the child's eyesight condition a few years later. So they interviewed parents of children that came to the eye clinic at the hospital. So we have children that were in darkness, night light, and room light, and then they're either nearsighted or they're not. So what are our observational or experimental units? And I put it there because if it's an observational study, they're called observational units. And if it's an experiment, then they're called experimental units. Okay. So in our case, either way, the units are going to be each child in the sample. The explanatory variable is what type of light, and that would be categorical. And there are 3 categories. Okay. The response variable is whether or not they are nearsighted. And it is categorical with only 2 groups, so binary. Now, your hypotheses, the null hypothesis is always going to be that there is not an association between what light the kids sleep with and whether or not they're nearsighted. Okay. Whereas the alternative is always going to be that there is an association. Okay. Now let's practice writing in symbols. We could say something like, well, we know that the proportion should be the same for each group if there's not an association. So we do pi for the dark equals pi for the night light equals pi for the room light. Okay. So if the population proportions were all the same, that would mean there's not an association. The alternative then, well, what's the opposite of that? We could have one that's different from the others, or they could all be different from each other. And it's hard to write that out in symbols. So we just say that at least one of them is different. So at least one I differs, or is different from the rest. Now we need to find our statistic and our p-values and everything. So we just come to the applet. And let me show you how you actually put this in. I don't think this one is built into it. So I'm going to click that I want to enter a table. Okay, and I need it to be a 2x3 table, which is what I had it on already. And then it helps me if I put in the names for everything. So I'll say like dark, night light, room, okay, near, and then I put in the data 18, 78, 41. We'll say not, 154, 154, 34. When you are done, double check your totals. So 172, 232, 75, 137, 342. That checking your totals is a really good way to make sure you put all of the numbers in correctly. Click use table. Don't forget that. Okay. Look at the segment and bar graph to make sure that's what you had in mind. So here's my 3 groups. We're nearsighted or not. Okay, all of that looks good. We click show the table. Okay. Let me clear all that out. And we want to choose our statistic to be chi-squared because it starts at mean group difference. You need to have it be chi-squared. And then it will show you, here's my observed chi-squared. If I click show the chi-squared output, then these contributions, that's each piece in that formula that we talked about before. You don't really have to pay much attention to that. You can see our p-values. I can shuffle once. So I get new data. I like to click the plot. And you're like, oh, those bars are really close to each other because there's no association. All right? And my new shuffle chi-square is 4. And I could just keep shuffling a few times. I'm getting pretty small values, like 5.3 seems to be my biggest here. So much smaller values than what we actually got for our statistic. Let's come back to our notes. So this is our statistic right here. Your observed chi-square. So my statistic is chi-squared equals 55.519. My simulated p-value, well, I have to count everything greater than or equal to 55.19. So make sure this is a greater than, put in your statistic and count, and it told me 0. Okay, we didn't get any samples that were that far away. Notice how far away my 55 was compared to the statistics I was actually getting when I shuffled. Now, is my sample size large enough to use the theory-based test? Well, all of these numbers right here, all of these numbers, they are all at least 10. So all the cell counts, or how many observations are in each cell, are at least 10. Okay, so we are good to go. Now we need our theory-based p-value. Remember, it's on here in 2 locations. You can look at your theory-based p-value right here, or right here. This is your theory. Whereas this red one is your simulation. So that's our simulation. This is your theory. So it says less than 0.0001. It just doesn't go lower than that on this applet. So for our conclusion, do we have evidence? Okay, well, our p-value was very, very small, so we would have very strong evidence that there is an association between the type of light and whether or not they are nearsighted. Okay. Who can we generalize to? If you think back to it, it said that this was people that came into the hospital, so not a random sample. So only generalize to similar people. Okay. And can we say cause and effect? No, this was not an experiment. Okay. The researchers didn't control how much light they had in their room. Okay. So not cause and effect. There's probably confounding factors. Like maybe whether or not the parents can see well. Maybe that's why they leave the light on, because the parents can't see well. Okay. Let's see. Which pairwise intervals are significant at the 5% significance level? Or like which pairs have a significant difference? So to that, we just come back to our applet and we click this 95% confidence intervals. Okay. And it will tell you these confidence intervals, when they're statistically significant, we'll even put this little star there. But I prefer that you don't remember that. I want you to remember to check to see if 0 is in the interval. So I want to check, is 0 in the interval? Okay. Or they're significant when 0 is not in the interval. So let's go back up. Before we look at it, I just want you to see, could you guess, looking at this plot, notice how they all seem different. So they all look different. I'm going to guess that they might all be different from each other. Let's see if I'm right now. Okay. So if 0 is not in the interval, that means they're significant. So looking at this, 0 is not in any of the intervals. So they are all significant. Or they were all significantly different. Okay. And then we might want to interpret them. Okay. So first, we want to compare dark versus night light. So let's come back up and find dark versus night light. That would be this first one right here of negative 0.308 to 0.155. So this one, I did word each one a little bit differently. Okay, so the first one says, we are 95% confident that there is a, so we're going to say 0.308 less to my 0.155 less probability, oh, so let's say lower. So 0.38 lower to 0.155 lower probability of a child being nearsighted if they sleep in the dark versus with a nightlight. Okay. The next one says we're 95% confident children that sleep in the dark. Okay. And there's a something proportion of nearsightedness than of children that sleep with a room light. So let's go find the one that compares dark to room light. So dark to room light is 0.564 to 0.320. And it looks like it's negative. So we'll say 0.564 less to 0.320 less proportion of nearsightedness than of children that sleep with a room light. And we're 95% confident the proportion of children that are nearsighted, so we want nearsighted, nearsighted is our response variable, is between something and something for night lights versus room lights. So let's come back up. So between our night lights and our room lights, it's going to be this 0.338 to 0.082. So 0.338 point lower and to 0.082 lower. Okay, so we're 95% confident that we're lower, it's a lower proportion than nearsighted if they sleep in the dark than a nightlight. Okay, and again, if we sleep in the dark versus with a room light, then we have a lower proportion. And if we sleep with a nightlight instead of a room light, then we have a lower proportion. So it looks like having lower light leads to lower proportions of people that are nearsighted. But again, we can't say cause and effect.